Our next video lesson is about looking at problems that relate to weight and mass. These are both level 1 problems or maybe level 2 problems, but any of these problems with weight and mass shouldn't be necessarily too complicated after where we've already been with Newton's second law. So let's take a look at our first example. Our first example is going to provide us an object of 12 kilograms that's sitting on the surface of the Earth, and it's going to ask us to determine the weight of the object. Now, we'll follow through the exact same steps that we normally would with any of our problems using the guess method. So we'll start out with our given. We know the mass of 12 kilograms. But as we read through the rest of the problem, it doesn't really give us anything explicit. So then we move on to our unknown, all right, and we're looking for the weight of the object. Now, for our purposes, weight and Fg, or force due to gravity, are exactly the same thing. Right? Weight is not W in this course. All right? Fg will represent weight or force due to gravity. You can use either. So our unknown here is Fg. So let's begin to put together our FBD. We have our mass here of 12 kilograms. We'll set up as positive, down as negative, just to keep things nice and simple, like we do, what we understand from math class. And then we'll add our force due to gravity, or our weight pulling down. Now, that doesn't seem to give us a whole ton of information, but we know that if we have a force, right, we can use Newton's second law, or sigma F is equal to m times a. From there, we need to make the relation, or the understanding, that sigma F is Fg in this instance. We only have one force acting on our object, and it's just the force pulling down, so that'll be Fg. From there, we're going to be able to say the mass isn't going to really necessarily change. We already know that. But then the question becomes, what's the acceleration that we have to use? Well, the acceleration that we have here in this problem is known as the acceleration due to gravity, or what we call little g. So we can come back, we can add that to our given. We know that on Earth, the acceleration due to gravity is 9.81 meters per second squared. So I've added that to my given information. Now I'm going to add it to my FBD. Anytime that you are asked to find the weight of an object on Earth, g will not necessarily always be given to you. That should be one of those things that you commit to memory, and you will, because we'll use it plenty over this unit and the following units. So just keep that in mind. You'll also find it on your equation sheet as you begin to move forward as well. From here, since we're trying to find Fg and we know m times g, we go right to the substitute step. Now, you'll notice that my g in my given is 9.81 meters per second squared, and the g that I substituted is negative 9.81 meters per second squared. That negative represents the fact that my g, or my acceleration due to gravity, is moving in the negative direction. Remember that acceleration is a vector, so it must have both a size and a direction. From there, we just solve by multiplying the two, one by the other, and we end up with negative 117.72 newtons. Now, that's one way to express our answer. The other way, if you don't want to have the negative in there, is to have 117.72 newtons moving downward. So this is a basic type of weight problem. You'll notice that any of our weight problems, we really only have three different things that we can solve for. So let's move into our second example here. Example number 2 now gives us two pieces of information. An object of mass 110 kilograms has a weight of 176 newtons when on the moon. Determine the acceleration due to gravity that is present on the moon. So, again, same steps as always. We'll go through our guess method, given, mass, and then our weight. From there, we'll set our unknown to be the acceleration due to gravity on the moon, or little g. We could actually note that with little g subscript m, if you'd like, for acceleration due to gravity on the moon. We'll make our free body diagram, again, just a simple shape, and then setting up as positive, down as negative, our force due to gravity there, and then we're trying to find out what this acceleration due to gravity is, or our little g. So again, we come back to our equation, and we make that transition, or that transformation, from sigma F is equal to m times a into Fg is equal to m times g, and that'll give us our weight equation there. From here, now we can begin to manipulate our equation because we're trying to solve for little g. So we need to get that by itself first and then plug everything in. So to do that, we're going to divide on both sides by m, and that'll cancel out the m's on the right-hand side, and it'll leave us with an equation of little g is equal to Fg divided by m. At this point, we've isolated the variable that we're looking for, so now we can begin to plug in what we know. We can plug in our Fg and our m. Again, I have negative 176 newtons that I'm plugging in because my force due to gravity is in the negative direction. Okay, again, force is a vector quantity, must have both magnitude and direction. So I take that, I can reduce, and it will give me negative 1.60 meters per second squared. So that means I have 1.60 meters per second squared of acceleration moving downward. So I can note it as it is there, or I can note it as 1.60 meters per second squared downward. This is essentially as complicated as these questions can really get because there's only those three pieces that you have to solve for. If you have any other questions, please make sure that you see your teacher as you move forward. We'll be doing some more practice with this in class.